This video gives a quick overview of how to use Terraform and Ansible together to automate the deployment and configuration of an F5 Big IP instance. Let's start with a quick overview. In this setup, we use the official F5 Big IP provider for Terraform and the F5 Big IP collection for Ansible. These official tools are developed and maintained by F5. Our setup uses Terraform to deploy an F5 Big IP instance on AWS and configure all necessary security groups for access. Then it outputs the public IP of the instance for use by Ansible. Ansible then connects to the Big IP instance using HTTP API over the management IP and configures the device by creating a pool with round-robin load balancing, assigning pool members with specific IP addresses and ports, and setting up a virtual server that listens on port 80 and applies HTTP and TCP profiles. Lastly, we set up a Jenkins pipeline to automate the process of running Terraform and Ansible. This simple setup allows us to quickly deploy and configure an F5 Big IP instance in AWS, making it easy to manage and maintain. Let's take a look at the demo. We begin by organizing the project. We have two main folders. One is for Terraform and one is for Ansible. We start with the Terraform folder. It contains two modules, one for infrastructure provisioning and one for configuration. The infrastructure module uses Terraform to create the AWS resources, while the configuration module uses Terraform to configure the Big IP instance. Let's look at the infrastructure module first. The networking TF file defines the VPC, subnets, routing tables, network interfaces, and elastic IPs. It creates a VPC with three subnets: external, management, and internal. Elastic IPs are created for the external and management interfaces. In the security groups TF file, we define the security groups for the Big IP instance. The external security group allows incoming traffic to the Big IP external interface from the internet. The management security group allows SSH and HTTPS access from specific IP addresses to the management IP. This is important for security, as it restricts access to the Big IP instance. The internal security group restricts access to Big IP internal interfaces. In the Big IP TF file, we create a Big IP instance using the AWS provider. We specify the AMI ID, instance type, network interfaces, and startup script. The startup script sets up the Big IP instance with initial configurations, such as admin user credentials. It also contains a hook to check the status of the Big IP instance and wait for it to be ready before proceeding to the next step. Here we also have a demo workloads TF file where we define two EC2 instances that will be used as pool members. In the configuration module, we have a Big IP VLANs TF file that configures the VLANs for the Big IP instance. It creates an external VLAN for the external interface and an internal VLAN for the internal interface. It also sets up the self IPs for both VLANs. The main TF file from the root folder is the entry point for Terraform. It includes references to the modules and passes variables to them. Here we also can find the Ansible inventory TF file. This file generates an inventory file for Ansible. Later we will use this to generate the inventory file for Ansible. This is how we connect the two tools together. Now we switch to the Ansible folder. We start with the inventory file. In this file, we use the Terraform provider plugin to generate the inventory file. It uses the Terraform state to get the necessary information needed to connect to the Big IP instance. The playbook we use does three things. First, it creates a pool named Demo Pool. This pool uses HTTP for health monitoring and round-robin for load balancing. Second, it adds a member to this pool using IP address and port. Third, it creates a virtual server that listens on port 80 and forwards traffic to the demo pool. It also applies HTTP and TCP profiles. We begin by running Terraform. First, we change into the Terraform directory, then we initialize and apply the plan. This step provisions the Big IP instance in the AWS cloud with all necessary resources. It creates the VPC, subnets, security groups, and the Big IP instance itself. The startup script runs on the instance to set up the initial configuration. Then it waits for the instance to be ready before proceeding. And finally, it applies the configuration to the Big IP instance. Next, we change into the Ansible directory. We install all dependencies before the run. Then we run the playbook using the generated inventory file to apply the initial configuration. When the playbook finishes, we can sign in to the Big IP instance using the management IP and check the configuration. We can see that the virtual server are created successfully and marked as up. The big IP instance is now ready to handle traffic. To test the setup, we open a web browser and enter the public IP of the external interface. We can see the web server page, which confirms that the big IP instance is working correctly. We can also open the AWS console and check the EC2 instance. In the network details, we can see attached management, internal and external interfaces. We can also see the assigned elastic IPs. After the initial setup, we show how to make changes to the infrastructure. For example, we may want to add tags to the AWS instance, which can help you understand costs and usage better. Tags are key value pairs that you can assign to AWS resources. They help you organize and manage your resources by providing additional context about their purpose or ownership. We already have a tags variable defined in the variables TF file, so we can modify it and add a new cost center tag. This tag can help you track costs associated with a specific project or department. After making this change, we run Terraform plan to see the changes. Terraform shows that it will add the tags to the instance. We then run Terraform apply to apply the changes. This updates the instance with the new tags. We can verify the tags in the AWS console by navigating to the EC2 instance and checking the Tags tab. We can see that the new tag has been added successfully. Now let's say we want to update the pool by adding another member. We go back to the Big IP UI to check the current configuration. As we can see, the pool has one member with IP address. To add a new member, we need to update the Ansible playbook. The playbook is responsible for configuring the Big IP instance. It defines the pool and its members. There is a section in the playbook where we define the pool members. We can add a new member by modifying the pool members list. After the change, we run the Ansible playbook again with the same inventory. Ansible connects to the Big IP instance and applies the updated configuration. Then we go to the Big IP GUI and check the pool configuration. We can see that the new pool member is added without affecting the existing setup. These steps show how easy it is to manage ongoing configuration changes using Ansible once the infrastructure is provisioned with Terraform. This approach is simple, reliable, and repeatable. It helps teams create environments that work the same way every time, whether it's for testing, development, or production. By splitting tasks, Terraform builds the infrastructure and Ansible configures it. It's easier to manage each part. Terraform keeps a state file with all changes, so it always knows what to add or update. Ansible only makes changes if something is missing or different. You can quickly update or roll back settings by editing the files. You can also reuse the same scripts to create new environments whenever needed. Automation also improves security by letting you define configuration in code, so there are fewer chances for manual errors. It makes all changes visible and trackable, so you can see who changed what and when. Overall, this makes your automation predictable, secure, and easier to maintain over time. Using Terraform and Ansible together is a good method for automating Big EP in environments where changes are rare. Terraform builds the cloud infrastructure, like networks, subnets, security settings, and Big EP instances. Then, Ansible handles the Big EP configuration, such as VLANs, self-IPs, pools, and virtual servers. This approach keeps the infrastructure and the Big IP settings separate, which makes things easier to manage and more organized. In environments where autoscaling or frequent changes happen, you can still use Terraform and Ansible, but you need extra tools. Terraform can create autoscaling groups and launch templates, but Ansible does not know when new Big IP instances are created. To fix this, you can use event-driven automation tools or CI/CD pipelines to trigger configurations when new instances appear. In these dynamic setups, Big EP features like config sync and cloud failover extension help a lot. Config sync keeps settings the same across all Big EP devices in a group, while CFE manages IP addresses and routing changes when devices are replaced. New Big EP devices can join the group and get the correct settings from others, which cuts down on manual work and keeps the system stable. At the end of the demo, we will explain how to integrate CI/CD with Terraform and Ansible. One of the most popular tools for this is Jenkins. Jenkins is an open-source automation server that helps automate tasks like building, testing, and deploying software. In our case, Jenkins will automate the use of Terraform and Ansible. Using a Jenkins pipeline, we can set up a job that runs Terraform and Ansible in sequence. This means that when we make changes to our code or infrastructure, Jenkins can automatically run the necessary scripts to apply those changes. First, Terraform will provision the infrastructure. Once that's done, the pipeline will run Ansible to configure the infrastructure. This setup enables continuous integration and deployment for both infrastructure and application configurations. You can also add extra steps to the pipeline, such as running code checks or sending notifications to team members when a job completes. This helps track changes and ensures everything is working as expected. When using an automation server, it's important to keep the Terraform state file secure. There are several options for securely storing the state file. You can use a remote backend like AWS S3, Google Cloud Storage, or HashiCorp Cloud. These backends offer secure storage, versioning, and allow multiple users to access the state file without conflicts. Finally, when the environment is no longer needed, you can set up a Jenkins job to destroy the infrastructure. This job will run the Terraform destroy command, which removes all resources created by Terraform. This helps clean up resources and avoid unnecessary costs. In summary, using Terraform and Ansible together provides a powerful way to automate the deployment and configuration of F5 big IP instances. With a few simple steps, you can set up a complete environment that is easy to manage and maintain. This approach allows companies to quickly adapt to changing needs and ensure that their applications and resources are always performing well. By using these tools, you can save time, cost, and increase efficiency in your infrastructure management. In this chapter, we will explore how to automate the deployment and failover of F5 Big IP in public cloud environments. We will cover how to use cloud templates to automate Big IP deployments in AWS, Azure, and GCP. Deploy failover configurations using the F5 Cloud Failover extension. Terraform and AWS Network Load Balancer to manage failover between Big IP instances using native AWS components. Ansible to scale applications on F5 Big IP devices. Deploying Big IP in the cloud can be complex, but F5 provides deployment templates to make it easier. These templates automate the setup of Big IP instances across different cloud providers, helping users save time and reduce errors. F5 offers CloudFormation templates for AWS, ARM templates for Azure, and GDM templates for Google Cloud. Each template can be customized to match specific deployment needs. Users can adjust settings such as network configuration, instance type, and other important options. The templates support different deployment models. Users can choose high availability configurations, failover setups, and multi-NIC designs. All templates are available in the F5 GitHub repository. They are updated regularly to include the latest features and best practices. Using these deployment templates enables automated provisioning of Big IP instances, including onboarding, licensing, network configuration, and application services. This reduces the time and effort needed to set up Big IP in the cloud, allowing users to focus on their applications rather than the underlying infrastructure. Next, we will explore how to automate failover for F5 Big IP using the Cloud Failover extension. This method is particularly useful in public cloud environments where traditional failover mechanisms may not be applicable. F5 Big IP Cloud Failover extension is one of the methods for managing failover that provides L3 failover in cloud environments by replacing traditional network-based failover mechanisms. CFE is based on iControl-LX and uses a declarative model, where a single JSON declaration via REST API sets up the failover configuration. During failover, CFE calls its internal API to update cloud infrastructure. It reassigns network interfaces and adjusts routing configurations to shift traffic to the active Big IP instance. When the original device is restored and designated as primary, CFE can redirect traffic back. The setup includes two Big IP devices configured as active and standby. CFE automates the failover process by managing the cloud networking components, such as elastic IPs in AWS or public IPs in Azure. It dynamically reassigns these IP addresses to ensure that traffic is routed to the active instance. To deploy CFE, install the package on Big IP systems, tag relevant cloud objects, and push a JSON configuration using the REST API. Why use Cloud Failover extension? Benefits of using Cloud Failover extension include standardized failover behavior across all supported cloud platforms, flexibility to deploy using Big IP runtime init, cloud-native templates, Terraform, or Ansible, Simplified lifecycle management, allowing big IP upgrades without reconfiguring high availability settings. In summary, Cloud Failover Extension enables automated updates to cloud networking components during failover events by dynamically reassigning IP addresses and updating routing tables to maintain active traffic flow without manual intervention. The second method for managing failover is to use AWS Network Load Balancer with F5 Big IP. This setup allows for automatic failover between two big IP instances, ensuring continuous service availability by routing traffic to the active instance using AWS NLB. The environment includes two VPCs connected via a transit gateway. The hub VPC contains two big app VE instances deployed in separate availability zones. Each instance has external, internal, and management interfaces. The app VPC contains application servers. The big IPs are part of a sync failover device group. Configuration synchronization and network failover communications use the internal interface. Both big IPs operate actively by managing different traffic groups. An AWS NLB is set up with target groups for each AZ. Each big IP external interface is registered as a target. The NLB uses health checks to route traffic to the healthy big IP instance. Failover is triggered by health check failures or loss of communication. When a failure occurs, the NLB health check detects it and reroutes traffic to the big IP instance that has taken over the failed traffic group. You can test failover by stopping the active instance or big IP service. Confirm that the NLB redirects traffic correctly to the new active instance handling the traffic group. This architecture supports automated high availability using native AWS components and big IP clustering. We move to the part where we scale an application on an F5 big IP device using Ansible. Scaling applications helps us handle more user traffic, improve performance, and maintain high availability as demand changes. By using automation tools like Ansible, we can scale quickly, avoid manual errors, and save time. We use the official F5 Big IP Ansible modules from the F5 modules collection. In this example, we create a new pool, add multiple pool members like application servers, and associate that pool with a virtual server. We can adapt this setup to dynamically scale our application by modifying the list of pool members, such as pulling data from an AWS EC2 inventory or Terraform outputs. Now, we walk through a sample Ansible playbook. In this playbook, we define a provider with our big IP server IP address and user credentials. We then specify variables for the pool name, virtual server name, and a list of pool members. The tasks include creating a pool with HTTP monitoring and round-robin load balancing, adding multiple pool members to this pool, and making sure the virtual server is configured to use the pool. The virtual server is defined with a public IP address, port 80, and uses AutoMap for SNAT with HTTP and TCP profiles. We can dynamically update the pool members list based on our cloud or orchestration environment to scale up or down. To scale down, we remove entries from the list and rerun the playbook. Let's run the script and check the result. After running the playbook, we can log into the big IP device and verify that the pool was created, the pool members are listed and healthy, and the virtual server is correctly pointing to the new pool. We should automatically trigger the script when we expect a spike in user traffic during scheduled scaling events, or when our monitoring systems show resource usage getting high. To automate this, it is possible to integrate the script into a CI/CD pipeline, use a scheduled job like cron, or set up triggers from cloud services such as AWS Lambda based on metrics like CPU or memory utilization. This way, the scaling process becomes automatic and keeps the application responsive. In this chapter, we learned how to automate the deployment and failover of F5 Big IP in public cloud environments. We covered how to use cloud templates, Terraform, Cloud Failover Extension, and AWS Network Load Balancer to manage failover configurations. We also explored how to scale applications on F5 Big EP using Ansible. These examples show how automation can be implemented and combined together to create a scalable and resilient infrastructure for applications running on F5 Big EP in the cloud. This chapter focuses on logging and troubleshooting in Terraform and Ansible. We will cover how to set up logging, centralize logs, and use logs for incident response and rollback. Let's start with Terraform. Terraform by default only shows minimal output in the command line. This keeps the output clean, but it also means you may not see helpful details when something goes wrong. To get more insight, you can enable detailed logging using the tflog environment variable. This lets you choose how much information Terraform should print. Trace gives you the most detail, while error shows only the most serious problems. For normal use, info is a good starting point. If you're trying to fix a problem, switch to debug or trace. By default, logs appear in the terminal. If you want to save them to a file, use the tflog path variable. For example, set tflog to debug and tflog path to Terraform log before running your command. This saves all debug messages into a file called Terraform log, which is helpful if you're running Terraform inside a script or automation pipeline. If you're integrating Terraform with other tools and need structured data, you can use tflog set to JSON. This gives you machine-readable logs at the trace level. But be careful, the JSON format might change in future Terraform versions, so don't depend on it unless you're ready to update your code when the format changes. You can also control what part of Terraform shows logs. Use tflog core if you want to see messages from Terraform's main engine. Use tflog provider to focus on messages from provider plugins, like the F5 Big IP provider. This is useful if you're debugging just the F5 part and don't want other noise. Finally, when using Terraform in scripts, it's a good idea to add no color to your commands. This removes color codes from the output, making the logs easier to read and parse. Use trace only when you need deep debugging. It slows things down and can create very large files. Logs may include cloud credentials, F5 device IPs, or config data. Never share raw logs publicly, and consider redacting secrets before pushing logs to team channels. Centralizing Terraform logs using ELK, Splunk, or Datadog helps teams monitor and troubleshoot infrastructure changes. With centralized logs, teams can search for errors and build dashboards to track changes and patterns. These logs also help link Terraform activity with deployments or incidents. Use log agents to send Terraform logs. For ELK, use FileBeat or Logstash to read logs and send them to Elasticsearch. Configure them to parse plain text or JSON logs. In Kibana, it is possible to create visualizations and alerts. For Splunk, use the Universal Forwarder or HTTP event collector. Set a custom source type and extract key fields for better queries and alerts. For Datadog, configure the agent to read log files and use tags to label them. Create alerts based on keywords like error in logs. Push logs after each run or stream them in real time. Short runs can push logs at the end. Longer runs may stream logs for live monitoring and dashboards. Use structured logging to make logs easier to parse. JSON logs are preferred. In plain text, add consistent prefixes and use regex to extract details. Filter logs before sending. Avoid forwarding all debug logs, which can increase costs. Send only info and above by default. Keep full logs locally if needed. Create dashboards and alerts to monitor changes and failures. Include metadata to track who ran what. Use these logs for audits and compliance. Avoid common mistakes. Don't flood your system with trace logs, don't log sensitive data, and ensure someone is responsible for monitoring logs. Test your logging setup with known errors to confirm alerts work. Terraform logs are very useful during incidents and for post-incident analysis. Terraform usually shows the resource name and error message in the CLI output when a resource fails. Once you find the failed resource, check how serious the failure is. If the change was not critical, you might only need to fix the configuration and run Terraform again. If it was a production change, you might need to undo or fix changes that were partially applied. Terraform logs can show which resources were changed before the failure. With Big IP, a partial apply might mean that some configuration changes are already live on the device. Use the logs and the Terraform state file to see what changes went through. If needed, you can manually remove those changes from the F5 or use Terraform taint to force Terraform to reapply them. If an incident happens, increase the logging level to get more detail. Run Terraform plan or apply again with debug or trace logging. This helps you collect more data to understand what went wrong. Treat Terraform logs as an important signal in your system. Set up alerts for issues when Terraform apply takes much longer than usual. Your logging system might help you detect this. Or when Terraform tries the same action many times before it succeeds, it could be a sign of problems. Even if the apply succeeded in the end, it's worth checking why the retries happened. You can use tools like Datadog or Splunk to detect unusual patterns in Terraform log volume or error messages. A sudden increase in errors might point to a bigger problem in your system. After an incident, use the logs to investigate what happened. You can match the timestamps in Terraform logs with application logs or network events. For example, if a change to Big IP happened at 10:05 a.m. and an app failed at 10:07 a.m., the logs help you confirm if the change caused the problem. You can also improve your Terraform setup using what you find in the logs. If logs show that resources were created in the wrong order, fix your Terraform code by adding depends on or adjusting references. If someone ran Terraform outside the usual process and caused a state conflict, add locks or rules to stop this from happening again. Always save the logs with your incident reports. Adding key parts of logs to tickets makes it easier for engineers to fix similar problems in the future. Let's look at how to set up Ansible logging, step by step. First, we need to configure Ansible config file. This file controls many settings for how Ansible runs. Under the Defaults section, set the path for a log file by adding this line. This tells Ansible to save all output from your playbook runs to that file. You will still see the output in your terminal, but now everything is also saved to a file for review later. To make the logs clearer, also add this line. This makes sure that variable values used in task names are shown in the logs. This helps tell similar tasks apart. Now let's improve the logging format using callback plugins. These plugins change how Ansible logs data. This gives you JSON format output, which is easy to search or send to log analysis tools. If you prefer YAML, use this instead. You can also enable multiple log-related plugins at once. These plugins add helpful details. Profile tasks shows how long each task takes. Timer adds timestamps. Log plays creates one log file per host in Ansible host directory. Make sure that folder exists and can be written to. To set where the log plays plugin saves its files, add this section. Now you'll see clean YAML output on the console and also get extra logs per host with timing details. By default, Ansible's logs already include timestamps. If you need different formatting, you can use or write a custom callback plugin. Finally, test your setup, run a playbook. Then check the log file to see if task names, results, and error messages are saved correctly. This makes it easier to troubleshoot and track what's happening, especially when automating tasks on F5 Big EP. When running a playbook, add one or more V options to get more details in the logs. For example, use one V option for basic details, use 3V option to see API calls, use 4V option for even more. But be careful. Using more detailed mode can reveal secrets in the logs, even if no log is set. So avoid using that level in production. In production, Ansible logs should be sent to a central system for storage, analysis, and alerts. Solutions include Elastic Stack, Splunk, Syslog servers, or cloud storage like Amazon S3. If using Red Hat Ansible Automation Platform, you can forward logs to systems like Splunk, ELK, Loggly, or Sumo Logic by configuring the controller settings. This provides job history and trend analysis. For example, you can send playbook logs to an ELK stack and visualize F5 device changes with Kibana. Without Automation Controller, use the Syslog JSON callback plugin from the Community collection to send events in JSON format to a Syslog server. Add this to Ansible config. This sends structured JSON logs to the example log server. Tools like Splunk or ELK can index these logs for search and alerts on failures or skipped tasks. If we write logs to a file, we can process it using collectors like FileBeat or a Splunk forwarder. Don't forget to set up log rotation to avoid filling up disk space. For separate logs per device, enable the log plays callback. It writes individual files under the Ansible hosts folder, which is useful for managing many F5 Big IP systems. It is also possible to upload log files to cloud storage like Amazon S3 or Azure Blob Storage after each playbook run. This is common in CI/CD pipelines where Jenkins archives Ansible log and artifacts to S3. Centralized logging helps connect Ansible events with infrastructure telemetry and supports setting alerts for failures or skipped tasks. This is important for maintaining the health of F5 Big IP devices. It also helps with compliance and auditing by providing a clear record of changes made to the infrastructure. Masking sensitive data in logs is important to protect secrets like passwords, tokens, and certificates. By default, Ansible logs all module arguments and results. This means secrets like the Big IP admin password could appear in log files if not masked. To prevent this, use the noLog, true attribute in tasks that deal with sensitive data. This tells Ansible to hide the task's input and output from logs and the console. For example, when creating a big IP virtual server and including login credentials, use no-log, true to avoid exposing the password. Ansible will show a note in place of the task output to indicate that details were hidden due to no-log. This makes it safe for secrets, but also hides all other task info. So only use no-log when necessary, not for every task. Be careful with high verbosity levels. If you run Ansible Playbook with 3 or 4V, some sensitive data could still show up in debug output. To stay safe, avoid these modes in production, or use other security tools. One useful tool is Ansible Vault. It lets you encrypt sensitive variables in your playbooks and inventories. Vault does not directly affect logging, but it helps keep the source files secure. Still, if a decrypted secret is printed during task execution, it could appear in logs unless no-log is used too. It's good practice to always apply no-log, true to any task that handles passwords or private keys. Ansible Lint can even enforce this rule. F5 Ansible modules also support secret masking. They automatically hide common sensitive fields, like the big IP password. You can also define your own secrets using the F5 secrets variable. This adds another layer of protection if you enable F5's debug logging. To sum up, always mask secrets in your automation scripts. Use no-log for sensitive tasks. Encrypt variables with Vault. Avoid verbose output in production, and rely on F5's built-in masking for extra safety. Ansible logs are not just for record keeping. They provide important information that helps operators make decisions. When automating F5 big IP devices, logs can be used for rollback, remediation, and redeployment. First, logs help with detecting failures. If an Ansible play fails, the log shows exactly which task failed, on which host, and why. Sometimes, an operator checks the log and fixes the problem or runs a playbook to fix it. In more advanced cases, monitoring tools read the logs and take action. Teams may also set up pipelines to watch for failures and run rollback or alert jobs automatically. Second, logs are useful for auditing and verifying changes. After a playbook runs successfully, you can read the log to make sure all intended changes happened. For example, if you're deploying 3 virtual servers and 2 pools, the log should show 3 changes for the servers and 2 for the pools. If anything is skipped or already there, the log will show OK or skipped. This helps spot missing changes or things that were already set up differently, which can point to configuration drift. Third, logs can show the differences before and after a change. Ansible shows what changed, but not all modules support it. Some modules only show the final state after a change. Saving this in the logs gives a clear snapshot of the updated configuration. You can compare it with the old state to decide if you need to roll back. Fourth, logs guide rollback decisions. Imagine deploying changes to multiple big IPs and one fails. The logs show which devices succeeded and which ones failed. If only some devices were updated, it may be best to undo those changes to keep everything consistent. Some teams follow a rule. If one fails, roll back the rest. The Ansible summary helps find these cases quickly without checking each device by hand. Fifth, logs help with traceability and compliance. In many environments, every change must be recorded. Ansible logs show who ran what playbook, when, and what it did. If a problem appears, you can check the logs to find out if a recent change caused it. This information is critical for fixing problems quickly. In conclusion, logs are a feedback loop for automation. They should be reviewed regularly, especially after big changes. This helps teams learn from mistakes and improve their automation processes.